So what we've got today is to talk about the law of universal gravitation. Um, and it's kind of a little bit of a tangent from circular motion, but it's going to be talking about orbits. And so orbits, you have to understand gravity in order to understand orbits, which are an example of circular motion. So we're just going to talk about law of universal gravitation today. Hopefully we're going to have time to do some practice problems with that. I went a little bit long first period, so I think that I've shortened it. We can get to that, but that's what we're doing today. So we're going to start with some notes. So go ahead and get out your notes. And you can label your notes for today Newton's law of universal gravitation. And what's really interesting, so you've probably heard the story. It's probably an apocryphal story. It's probably not true. But you've probably heard the story about Isaac Newton and the apple that fell on his head, and then he used that idea to like think about what gravity was. Well, the real story is actually quite a bit more interesting than that. The Newton's law of universal gravitation comes about with one of these really brilliant insights that Newton had. Was the idea that the physics that governs planets is the same as the physics on Earth, right? So this is what's called the Newtonian synthesis. It's called the Newtonian synthesis because it was kind of thought because there was kind of like the study of the heavens, right, of the stars and the planets. And then there was the study of terrestrial physics, but it was assumed that what governed the heavens was totally different than the laws that govern us here on Earth. But Newton was the first to kind of think about like what goes on in space. As a matter of fact, the whole idea of space as a place to go wouldn't have even made sense before Newton, because the stars were just points of light in the sky. And the planets come from the Greek word that means wanderer. Planets were just points of light that wandered across the sky. But Newton had this idea to think about, what if the physics of all those things are the same as the physics on Earth? And to think about that, he did this thought experiment. And he started by just thinking about the moon. So he did this thought experiment. So here's the Earth. By the way, there's a common misconception that people thought that the Earth was flat until like around Newton's time. It's not true. At least in the West, the idea that the Earth was round has been known, for probably 5,000 or 6,000 years now. So it wasn't that people thought that the Earth was a flat, but people did think that the Earth was the center of the universe, and that things like what we now call gravity, they just said that things tended to go to the center of the universe. And since the Earth was the center of the universe, all things tended to go to the Earth. But here was Isaac Newton's thought experiment. He said, okay, imagine a really tall mountain. Imagine that you had a mountain on the Earth that was really tall, like that. Then imagine that you took a cannon and you put it at the top of the mountain, and you fired a cannonball off the top of this mountain. So usually what happens is what we expect out of any projectile, right? It's just gonna make a parabola and it's gonna hit the ground. If I fire it a little bit faster, it's gonna do the same thing. It's gonna hit the ground a little farther away. But what if I threw it so fast, or I launched it so fast, that as it fell, the Earth curved out of its way? What if you had something that fell around the Earth? And this is what we now call an orbit, right? But this is what was really interesting about what Newton said, and this is the core of the Newtonian synthesis. The gravity that pulls things on Earth down is the same gravity that pulls the Earth around, or sorry, pulls the moon around the Earth. And then from there, it's only a little bit, it's only a small logical step to say that there's also this same gravity that pulls the Earth around the sun. So the Newton's law of universal gravity, it's universal because Newton is applying this idea of gravity to everything in the universe, not just the things on Earth, right? Everything in the universe, he says, obeys this law of gravity. And that orbits or planets, the motion of planets, the motion of the moon and everything is nothing more than objects falling around other objects, right? Pardon me, the moon falling around the Earth. So from this idea, he came up with the law, and the law has three parts that can be summarized in one equation. So I'm going to give you the three parts of Newton's law of universal gravitation first. The first part is that all objects with mass attract all other objects in the universe with a force called gravity. All objects attract all other objects. This force of gravity is dependent upon two things. So we're going to say the force of gravity is proportional to the product of two masses. So if you have two things, you take their masses, you multiply them together, gravity is going to be proportional to that. And the last part is the force of gravity is inversely proportional to the square of the distance between the objects. So basically what does this say? This says if you've got objects that have more mass, you have more gravity. If you have objects that are closer together, you have more gravity, right? So the further apart things are, the less gravity there is. And then we can summarize this in one equation, and that equation is the force of gravity is equal to, leave a spot here because I'm going to put something there in a second, but I'm going to put the product of two masses on the top, and I'm going to put the distance at the bottom. I'm going to refer to the distance, though, as a radius, because oftentimes we are talking about circular motion. So I'm going to call it R, but R just stands for the distance between objects. And this has to be in meters. And the M1 and the M2, they stand for the masses, and those need to be in kilograms. And then to make this all work out, we got to put one more thing here. This is the constant of proportionality, but we're going to call it capital G. Now, it's important that it's a capital G because we've already talked about lowercase g, right? Lowercase g is the 9.8, but this is something else. This capital G is what is called the universal gravitational constant. And basically, it tells how strong gravity is. I'm going to tell you what the number is here in a second. The first thing I'd like to do, though, if you don't mind, before I do that, I want to take sort of an informal poll, and you can just type your answer in the chat. I just want to kind of a vote. Do you think of gravity as a strong, relatively strong force or relatively weak force? So just in the chat, put what you think. Do you think of it as a relatively strong force or relatively weak force? All right, fair enough. So we're mostly saying weak. Can somebody give me an argument for it being weak? Because actually, usually I get that it's a strong force. No one want to make an argument for why gravity is a weak force?
I honestly just knew beforehand that it was weak.
Fair enough. Fair enough. Yeah. How about this? Anybody else want to try for an explanation? I'm going to do a demonstration real quick. I'm going to show you how easy it is to defy gravity. You ready for this? Okay. I just did it, right? As a matter of fact, the muscles in my pinky finger are stronger than gravity, right? I can defy gravity just with the muscles in my pinky finger. Gravity is an incredibly weak force, okay? There's a couple ways to think about this, right? First of all, if you look back at what the law says, right? The law says that all objects attract all other objects. If that's the case, then these two pens should be attracting each other with gravity. And they do. They do attract each other with gravity. However, it's just so weak. It is incredibly weak. You have to have something the size of a planet, or at least a moon, before you get enough gravity built up that you even recognize that it's there. But even then, even you imagine something with so much mass like the Earth, it is very easy to overcome the gravity. Almost any other force in the universe is stronger than gravity, right? The forces that hold my body together have to be stronger than gravity. Otherwise, I would just be a puddle on the floor, right? So gravity is actually a very weak force. How weak is it? It's given by this universal gravitational constant. Tells us how weak gravity is, and it's always the same everywhere in the universe. It's 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. I'll talk about that unit in a second. But for right now, I just want you to know that the universal gravitational constant G is equal to that number. That 10 to the negative 11th means that it's 0.00000, like 11.0667 Newton meters per kilogram squared. It's extraordinarily weak. All right. Any questions here? If you, I'm going to give you a second if you need to. Hopefully you've got a calculator handy. If not, go ahead and grab one. If you need to step away and grab one, do that. It's going to be helpful to have a real calculator and not just a phone calculator, because we're going to be doing some stuff with scientific notation. Well, I'm going to do an example problem to illustrate how weak gravity is, but also to get us used to solving problems with scientific notation. So here's the problem. Imagine that you've got a bowling ball, and we're going to say this bowling ball is 5 kilograms. Then let's say that we have a car. I should draw the car as being bigger than the bowling ball, I suppose. That's my weird car. Okay, whatever. This car we're going to say is 950 kilograms. And we're going to say that they are separated by a distance of, let's say, 75 centimeters. Let's calculate how much gravity is acting between those two objects. All right, so we've got our equation. So the math of this equation is very easy. It's the only thing that we need to practice is using our calculators. But I'll set up this equation for you, right? So we got the equation: F equals G m1 m2 divided by r squared. So what we've got to say here is we always know what G is. G is always that number that I put up here, right? And you don't have to memorize that. I'll always give that to you. But G is going to be 6.67 times 10 to the negative 11th. I'm just going to put units here for now. The first mass is 5 kilograms. The second mass is 950 kilograms. And then we have to divide by, again, we call this R because a lot of times it's a radius, but in this case, it's not really a radius. It's just a separation. It's 75 centimeters. Now, I can't actually put 75 centimeters because remember I said we want our distance in meters. So it really should be 0.75 meters squared. All right. If you've had chemistry before, you probably know how to do scientific notation on your calculator. But if you either haven't had chemistry or you don't remember how to do it, I'm going to give you a quick crash course in that, right? What you're looking for in your calculator, so if you've got a calculator like mine, there's this EE button. So it's above my x to the negative 1. It says EE. You're either looking for a button that says EE, or it might say EXP, or it might say times 10 to the n or something like that. And the way you enter this into your calculator is you use that exponential button. That stands for times 10 to whatever the next number is, right? So 6.67 e negative 11 means 6.67 times 10 to the negative 11th. And generally, I put a parentheses around my numbers so that they don't get confused. So I've got 6.67 times 10 to the negative 11th times 5 times 950 divided by 0.75 squared. If you would do me a favor and try and get this in your calculator, so I'm getting 0.00563, or the other way I could write it, your calculator might give it in scientific notation. So 1, 2, 3, 4, 5, 6, 7. So it's either that or 5.67 times 10 to the negative, what did I say? Negative 7th. So go ahead and try this in your calculator and just give me in the chat, just give me an I've got it when you've got it, or ask a question if you're not, because I just want to see how we're doing with the calculator.
Oh, what mode should the calculator be in?
It doesn't matter. You're talking about degree or radian?
Yeah.
It doesn't matter.
Okay.
I
had it.
We're doing sine cosine stuff.
I had it in like science, I think, and it was giving me like 6.67 times 10 to the negative 11th, and I'm like, that's what I put in.
Oh, I see. You got to put the whole thing in. If you just put one thing in, it'll just give it back at you. But you see how I put the whole thing in, like I multiplied them all out and then divided. Does that make sense?
Yeah, it does.
Yeah. Cool. So the only other thing I'll show you real quick, and I don't necessarily expect you to show your units every time, but I just want to show you why these units are so strange, Newton meters squared per kilogram squared. It's because I've got 2 kilograms here, right? So they have to cancel out the kilogram squared. And then I have a meter that gets squared here, so it cancels out the meter squared. And I'm left with newtons, which makes sense for a force. So this is why we don't notice the gravity between most objects, right? Because that's an extremely small force. So we usually are just safe to ignore it. All right, any other questions here or any other calculator questions? I'm going to show you one other type of problem you can do with this. So I'm going to tell you something first of all. I'm just going to give you some background information. First of all, the radius of the Earth is, you're going to need this in a second. So the radius of the Earth is going to be 6.38 times 10 to the third kilometers. And the mass of the Earth is going to be 5.98 times 10 to the 24th kilograms. So these are just things that the problem will tell you. I'm going to say find the acceleration of gravity on Earth. Now, let's just stop for a second because we actually already know the answer. What's the answer?
9.8.
9.8. So this is going to be what we're going to test to see if we can get this, right? So pretend for a minute that you don't know that, right? This will just be how we'll check our answer when we're done. Okay, if we want to find the acceleration of gravity on Earth, right? So acceleration of gravity is little g. So the way we can, let's say that you were given the radius and mass of a planet and you wanted to find its acceleration of gravity. We now know two ways to do that, right? We know two ways to find the force of gravity. We know that Fg equals mg, and we also know that Fg equals g m1 m2 divided by r squared. Now, if you'll notice, this we call the law of universal gravitation because it's true everywhere in the universe. This is only true like on whatever planet I'm talking about, right? But they are both telling me the force of gravity. So what I could do is I could say, okay, imagine that I'm standing on the Earth here, right? And I want to drop an object. Sorry, you can't see that. That's me dropping an object on the Earth. We should be able to calculate what the acceleration is, what g is, right? And the way we do that is we combine these two equations together. And we say that mass times g is equal to g, and I'm going to avoid the subscripts for a second. I'll show you why in a second. The g mm over r squared. Now, the reason why I didn't include the subscripts is I want to think about what are the two objects that are attracting each other in this case. Well, one of them is the Earth. So I'm going to call that ME. What's the other mass? It's whatever object I'm dropping. So I'm going to call that MO, right? Which mass is this? Which mass do we usually plug in when we're using this equation? Do we plug in the mass of an object or the mass of the planet? Probably just the object, right? But look what we've done. Now we've gotten so that we can cancel out our mass of the objects, and we've got an equation for the acceleration of gravity. So we should see if we can get this to work, right? If we can get 9.8 out of this formula. So G equals, big G is always that same number. I told you the mass of the Earth up here is 5.98 times 10 to the 24th kilograms. Now, got to be careful with the radius of the Earth. Radius of the Earth is 6.38 times 10 to the third kilometers. How many meters is that? I know. Well, remember there are 10 to the third meters in 1 kilometer. So this is just like saying 6.38 times 10 to the 6th meters. So just remember you can, if it gives it to you in kilometers, you just have to add 3 to the exponent. So go ahead and try typing this in your calculator and see if we can get 9.8 out of this. One thing to be careful about is make sure to square your denominator. I don't know if you can see that, but I got pretty darn close. Any questions about this? Oops, sorry. If we're doing really great on time, this is good. So there are 2 practice problems today. So in the day 39 assignment, there are 2 practice problems here. I included what you would have in person if I'd seen you in person, but here are all the equations we've talked about. I included the mass and radius of different things here that you might need. So what I'd like you to do is I'd like you to try these 2 problems. You can check your answers down here when you get there. And just like we were doing before, ask me questions as they come up, or when you're finished with both these, you can turn it in. And then once you turn it in, you're done. And also, if anyone's got questions on getting this 9.8, let me know too.